we should investigate the inclusion-exclusion formula by looking at specific cases to build intuition for where it's likely to be useful. Before we launch into calculations, it'll be wise to step back and take a look at it from a vantage point, a philosophical vantage point, as it were, to see where this is positioned and where it is likely to be useful. On the left of the inclusion-exclusion formula, what I've got is the probability of a sum. What we're computing is the distribution of the number of occurrences of certain events. So far, so good. That looks like it might well be useful in many contexts. What about the right-hand side? Well, that's where we have a formidable-looking alternating sum. The terms of the sum, on the other hand, involve intersection probabilities. And so immediately, from a philosophical point of view, this suggests to us that where inclusion and exclusion is most likely to be profitable is where the events are independent or perhaps mildly dependent. In other words, the degree of dependence is not too strong. If that is the case, then we may be in with a shout at computing these intersection probabilities, because you recall that independence is a rule of products. Intersection probabilities devolve beautifully when there's independence. So this suggests that we should start by looking at independent cases first. Following the prescription of George Polya, we're going to look at the simplest of these cases to see if we can understand where this leads us. And as we shall see very shortly, an old friend is going to resurface from these considerations. So accordingly, let's start by specializing an event family, A1 through AN, in some abstract probability space. Let's specialize it to the case where the events now are independent. Let's make further simplifications here and assume further that not only are these events independent, but they all have the same mass. They all have the same probability. Inevitably, we'll call this probability little p. Now, what does inclusion and exclusion tell us in such a setting? Now, before we dive into an analysis of the formulation, let's take a look at the generic terms on the right of the equation. We're going to sum in an alternating fashion for a given value k, the terms sk, sk plus 1, sk plus 2, and so forth. The generic term on the right is of the form sk plus j. Now, what does the inclusion-exclusion sum sk plus j portend? Well, the formulation is admittedly formidable. But in words, it's quite simple to describe. Pick any k plus j of the events A1 through AN, look at the intersection, compute the probability, and sum such probabilities over all choices of k plus j events from the collection. Okay, now where does this lead us? The summands on the right deal with the probability of an intersection. Independence is a rule of products. The probability of an intersection in this case is going to be exactly the product of the individual probabilities. Now, there are k plus j events in that intersection. Each of them, by our assumption, has got probability p. Independence says we're going to multiply p by itself k plus j times. In other words, we're going to accumulate for the probability precisely p to the power k plus j. Once you've done that, every probability in that sum is equal to p to the power k plus j. How many terms are there in the sum? Well, we have n events to start with, and we're selecting all possibilities for k plus j. In other words, there are exactly n choose k plus j terms in the sum, and each of the summands contributes exactly p to the power k plus j. And there you go. In the case when things are independent, the inclusion-exclusion sums simplify magically, beautifully. The proper vantage points frequently adds a magical clarity to an otherwise dim and murky business. Now let's dive into the formulation. So what do we have? We've got various inclusion-exclusion sums which have got a particularly simple binomial character. What are we trying to do with these? Well, we're going to look at the indicators for the various events. x1 is the indicator for a1, x2 for a2, xj for a generic aj. We're going to look at the sums of these indicators. x1 plus x2 through xn is going to tell us how many of the events occurred, and that is precisely the domain of the inclusion-exclusion theorem. The theorem tells us the probability that precisely k of the events a1 through an occurred is given by an alternating sum starting at sk, and then involving sk plus 1, and then sk plus 2, and so forth. Each of the terms, sk plus j on the right, has got a simple binomial formulation. Let's promptly write it down. And now, inside the sum, I've got something which looks a little forbidding initially, because I've got a product of two binomial coefficients. But that should look familiar. We've seen something like this not very long ago. In fact, in the last video lecture, we saw precisely a combinatorial identity for a product of binomial coefficients of this form when L was some generic number bigger than k. And if we select L to be n exactly, then we can just write down what we discovered in our combinatorial identity. Writing this product of binomial coefficients down as a different product of binomial coefficients, this time with j appearing only in one place. Let's plug it in. And now I'm going to do a little bit of, let's call it housekeeping. I'm going to rearrange terms and color code them. First, observe, I've taken a product of two binomial coefficients and replaced it by my combinatorial identity. Next, I've taken p to the power k plus j and rewritten it as p to the power k times p to the power j. And finally, I've color-coded things blue and green. The objective being that I want to isolate terms that do not depend upon j, pull them out of the sum. These are the terms in blue. And identify precisely those things in the sum which are going to devolve upon the choice of j. Now, the terms in blue, n choose k times p to the power k, don't depend upon j. They can be pulled right out of the sum. Let's promptly do this. The terms in green inside the sum depend on j, and of course they cannot be pulled out of the sum. But they're of the form minus 1 to a power j times p to the power j. In other words, you have both terms to power j. Let's combine them and write it simply as minus p to the power j. Now take a good look at that sum on the right-hand side. Does this look familiar? Of course it does. This is another instance of the generic binomial theorem. Remember, 1 plus x to the power n can be written as a sum of binomial coefficients times powers of x. If we identify m, in this case, with n minus k, and we identify x now with minus p, everything is ripe for an automatic application of this binomial theorem. Now, let's properly do this. We get n choose k times p to the power k times 1 plus x replaced by minus p is 1 plus minus p, the whole to the power n minus k. Now, does this look familiar? Assuredly it does. This is something we spent a lot of time playing with over the last couple of weeks. And you'll say, aha, this is a binomial distribution. This is exactly the binomial probability attached to the number of successes, k, in n tosses of a coin whose success probability is p. 1 minus p, of course, is a failure probability. We rediscovered the binomial distribution magically, beautifully. What we have just discovered is that the number of occurrences of the events a1 through an, in other words, the sum of indicators x1 through xn, is governed by a binomial distribution corresponding to n tosses of a coin whose success probability is p. This is lovely. It is always gratifying to have old acquaintance come back to us. In retrospect, was it surprising? And we think about it and say, what does this remind us of? Of course, of repeated independent trials. If you imagine that each of the events A1 through AN represented success or failure outcomes for each of n coin tosses, n distinct independent trials, then this is precisely the setting. And now, of course, it is not at all surprising that we've discovered the binomial distribution. What we computed in the number of events that occurred is precisely the number of successes in tosses of a coin. And so the binomial has emerged. Now, this is a lot of work to get to the binomial distribution, and assuredly our earlier approaches were much faster and much more to the point. They got us to the binomial distribution quickly and efficiently. Was there any work in this exercise? Of course there was. The fact that the binomial distribution emerges when you have independence in these events, A1 through AN, is gratifying and is suggestive that this line of thought can now be extended beyond purely combinatorial arguments. Remember, when we looked at the binomial, we developed the distribution from purely combinatorial principles. This now tells us that if we go beyond the province of independent coin tosses, if we go into a setting where there is a modicum of dependence, perhaps not excessive, that this formulation is going to lead us to answers beyond the binomial, to be sure, but perhaps not too far from it. And in particular, this suggests that quantities that emerge from the binomial might well hold on a much larger scope and scale. And in particular, Poisson's beautiful approximation to the binomial distribution in the context of rare events that he discovered in 1837 when he was talking about jurisprudence in France. This might well be something that emerges and holds true more generically. At any rate, this is well worth investigating. This is up next.